confidence interval, the statistic that will be used in the future more than anything else. That's my prediction now. I am making a prediction of the use of confidence intervals with a tool that is used to make predictions. If you have a good understanding of confidence intervals, you really understand stats. I like to exaggerate. I'm known for my hyperbole. And one of the things I'm going to argue right now is that stats make us superhuman. So, how do stats work? You're going to learn this throughout a little bit today and a lot in our next class. Stats allow us to make inferences about the population. So, we gather a sample of data, and from that sample of data, we don't just make conclusions about my sample of data. For example, when I run studies on just Regis students, I don't get to publish studies that just talk about Regis students because nobody in the world outside of students at Regis really cares about the psychological processes of only Regis students unless they apply to all humans. And so essentially what I'm doing is I'm gathering data from Regis College students and I'm making inferences about all humans, all Americans, maybe even all Coloradans. And stats allow me to make a guess as to what these population values are. I think that's really important. Through our sample, we're trying to understand the true population values. Now, if you think about that, how would I ever know anything about all Americans? I would have to measure every single American that's alive at this moment, right? That's hard. I'm going to argue impossible. I'm going to argue that requires superpowers, like being an omniscient being, like having the powers of the Greek gods or having the power of God, the all-knowing power of God. That is impossible, except we've developed statistics that allow us to measure information from samples and make conclusions about populations. So our stats really do make us superhuman. So what is a confidence interval? Now, the confidence interval is really tricky to define. A lot of really good statisticians argue they don't understand what it means. But we all agree on this one definition. If you ran your experiment 100 times, 95% of your 95% confidence intervals of any statistic, mean difference, standard deviation, anything, would include the true population value of your statistic. While it's incorrect to say this next definition, it wasn't until recently that I realized how wrong it was, but it helps you understand the importance of a confidence interval. It's okay to think that your confidence interval has a 95% chance of including the true population value. That's a way a lot of beginners think about it. Now, it's wrong, so a better way that I would say is that there's a very high chance that your confidence interval includes the true population value. Just say that. There's a very high chance that the true population value that I am seeking is included in my 95% confidence interval. We don't know exactly how high of a chance, don't worry about that, but ultimately at the end of the day, this confidence interval allows us to have an understanding of what the true population value is. Remember what I said in the previous slide. That's very hard for humans to do. You are now gaining powers of, gods, of omniscient beings, right? Like you're gaining a very important superpower. If you were a Marvel superhero, you might be Dr. Statistician. I don't know. That was a bad joke. So, what is in a confidence interval? First, let's talk about the confidence intervals that matter for this class, for this discussion, for this conceptual unit that we're working through. It's the confidence interval of the mean difference. We are interested in control versus experimental groups. We're interested in that mean difference. That's how I'm going to talk about it for right now. That's the most simplified form of science that we respect. And so the confidence interval we're talking about is the 95% confidence interval of the mean difference. You can have other 95% confidence intervals, standard deviations. You can even have confidence intervals of p-values. But ultimately, we're just going to focus on the 95% confidence interval, the mean difference. So here's our interval. And they're often presented with these brackets. There's two numbers. One's the lower limit, one's the upper limit. All right, so that's a confidence interval, -10 to +10. What do we know? The center is our sampled mean difference. So in this case, our sampled mean difference would be 0. One limit is your worst case scenario for your hypothesis, and the other limit is your best case scenario for your hypothesis. When I calculate my sample mean difference, I do it such that larger numbers support my hypothesis. That's how I do it. You can choose experimental minus control. You can choose control minus experimental. It doesn't matter. But in general, what I do is I make sure that my subtraction matches my hypothesis. And so what we get there is we get positive values support, negative values go against. So when it comes to what's our best case scenario? Well, with my confidence interval, 10 is the best case scenario. Right? What's my worst case scenario? Well, in my confidence interval, it's -10 because that's going against my prediction. So you got this spread. The limits together, I'm going to call it the spread, but you got your worst case scenario and your best case scenario. And you have to figure out, does this mean I have bad measurement error? Does this mean I have a bad experiment? That's kind of what you're looking at and what we'll get into today. Additionally, a lot of folks are so heavily focused on p-value. One of the greatest things that I will tell you is, while I'm not a huge fan of p-values, you'll see why in a few slides. If your confidence interval of the mean difference includes 0, you know that your p is greater than 0.05. If your confidence interval does not include 0, you know your p is less than 0.05. So you can make that determination of statistical difference or statistical significance, right? I think that's really important. So our confidence intervals, very simple idea. How you set them up matters. I do mine such that the positive values are in line with my hypothesis. The negative values are against. So here we can see that we have worst case scenario is against, best case scenario is in favor of my hypothesis. The center of this interval is our mean difference from our sample. And finally, if it includes 0, then we know the p-value is greater than 0.05. If it doesn't, we know that our p-value is less than 0.05. So how do we get our 95% confidence interval? Essentially, we take our mean difference. This is a new example. So we have a mean difference of 5. We apply the normal curve formula to it, and that requires your standard deviation and some other stuff. We'll get into that a little bit later in the course. And we find the middle 95% of this normal curve centered around our mean difference of 5. One of those limits is our upper limit. One of those is our lower limit. In general, what I'm looking for is I'm trying to figure out how bad is my estimation of that mean difference. Do I actually have a good grasp of what that true mean difference is in the population, or do I really not know much? So what matters so far? Your mean difference equals your best estimate of signal. We talked about that in the previous lecture. We apply our known standard deviation to the normal curve, and we apply it in a way that I'm not showing you the formula today, but I just want you to realize that these are applied. And from that, we get our upper and lower limits. And what we know is that the true population value is likely contained in this interval. Saying that it's a 95% likelihood is wrong, but saying, okay, if I reran this experiment 100 times, 95 of them would include the true population mean. That's what we know so far. So there are 3 important aspects of the confidence interval of the mean difference. First thing, the middle of the interval, which is not stated in numbers, is your sampled mean difference. The second thing, if your confidence interval includes 0, your p-value is greater than 0.05. If your confidence interval does not include 0, you have a significant p-value less than 0.05. Now let me talk about statistical significance just in a memory sense. Small p-values are significant. Small are significant. Small are significant. P less than 0.05. That means you have observed a real difference between your control and your experimental conditions. Small is significant, real difference. Small is significant. Small is significant. Small is significant. You've observed a mathematical difference. When your p-value is greater than 0.05, that's large, right? So it's not small, Not small is not significant. Not small is not significant. Not small is not significant. Small is significant. Not small is not significant. Small is significant. Not small is not significant. Remember that. But the real important aspect of a confidence interval is the spread. The spread. You have one limit that's the worst case scenario for your alternative hypothesis. These are the hypotheses you made when you were designing your experiment, the thing you believed would happen. So one case is going to be the worst case scenario for your alternative hypothesis. The other limit is going to be the best case scenario for your alternative hypothesis. You also need to realize that the larger the spread, the worse your measurement error. But let's take that example from before where a 95% confidence interval was from -10 to +10. That doesn't feel good, right? We know zero's in there, so we know, right, that our p-value is greater than 0.05, not small, not significant. The mean and control group are not mathematically different. That's what we know from that previous confidence interval of -10 to +10. Best case scenario, there's a 10-point difference in favor of my hypothesis. Worst case scenario, there's a negative 10-point difference in the opposite direction of my hypothesis. If you assume that we used a 5-point Likert scale, these differences are off the chart. This could be the largest difference in favor of my hypothesis ever found. It's not even possible it's so large. Or this could be the largest difference that goes against my hypothesis that's even larger than is possible. So literally in this case, I would know nothing. But it is kind of hard to interpret the spread. And so I'm going to show you an art for interpreting the spread. So now we're on the spread. What I do and what I'm going to suggest is always, and I will always give you the data to be able to do this, is convert your 95% confidence intervals of the mean difference to Cohen's d's. Okay? So going back to that discussion from the previous lecture, a 0.2 Cohen's d is small, worthless. That's essentially how we think about it. I'm not going to lie to you here. I've already talked about the nuances there, but let's be real. When you're reading a paper, it's been published, a small Cohen's d is not a good thing. So like for us, when we have our hypotheses, right, a small Cohen's d is a point for us to have reservation about our hypothesis. Like, oh, wow, this is a really small effect. Do I want to put out policy information for others to use or medical information for others to use on my tiny little effect? We have an ethical responsibility in some ways to make sure we're thinking about the context. And for most contexts of the research that we're going to do, this sort of like investigative, testing out new ideas, we need to realize that our research can be put into policy or medicine, and so we have to think about our effect size. And for the most part, we want a large effect size. For example, when you're developing a vaccine, you want a large effect size. This makes me think, there was actually an HIV vaccine tested about 20 years ago, and they published a paper on it. And they showed a significant difference, but the effect size was so tiny that like it would have reduced your chance of infection with HIV by like 0.1% or something like that. But because they had such, I'm not going to go into all the reasons why, but they had a significant difference that was a very small effect size. And so this is why we have to start moving away from just p-values only. Now we know 0.5, that's the average effect in psychology. Hey, if it's good enough for the field you're in, and neuroscience as well, if it's good enough for the field you're in, it's good enough for your research. And then 0.8 is large. Those are happy days. Anything above 0.5 is going to be a happy day. Now, here's an example, just a theoretical one. 95% confidence interval, the mean difference is from -0.5 to +0.5. Is this bad measurement? My answer is I have no idea. It depends on my standard deviation. I have to convert these mean differences to Cohen's d's. And I'm choosing the standard deviation of 1 because I don't want you to get caught up in math confusion, right? The standard deviation is not always 1. I'm just stating these two standard deviations are 1 from control and experimental groups, or average standard deviation is 1. 0.5 divided by 1 is 0.5. So our 95% confidence interval of the Cohen's d is -0.5 to +0.5. So what do I know? I know my p is greater than 0.05. That is non-significant, large, small, significant. That's That's large, right? Anything greater than 0.05 is large, so that's a large one. Not small. Small is significant, so not small is not significant. Oh, that's a good way. Not small, not significant. Yay, small, significant. There we go. My mean difference, my actual mean difference is 0 because I set up this data, it's made up. Worst case scenario. Medium effect in the opposite direction than my prediction, your prediction. Best case scenario, medium effect in the direction we predicted. Do you have precision in your estimate? Let's look at this visually. Okay, so the red represent effects that cannot be. So this effect cannot be a large effect for my hypothesis or a large effect against my hypothesis. It is not in that range. But what can the true population mean difference actually be? Well, it can be a average effect in favor of my hypothesis, a small effect in favor of my hypothesis, no effect, a small effect against my hypothesis, or a medium effect against my hypothesis, or average effect against my hypothesis. So medium and average are actually in there on purpose. I want you to see that that's the same thing, right? It's the same thing. I'm also a little sloppy, so you can judge me a little bit. Mark me down for not being perfectly organized. I don't mind. But ultimately, when we're looking at this, you're like, oh, wow. There are 1, 2, 3, 4, 5, 6, 7 possible effects according to Cohen. And this effect, in this true population effect, the true effect in the population could actually be 5 of these 7 effects. Is this precise? Do I have a precise estimate of my mean difference? Oh no, not at all, right? Like, I have no idea. All I really know is that this effect is not a large effect. That's all I know. But other than that, it could be anything. It's not large, but could be anything. That's not what we call precision. Do we have precision? No. I gave it away in the past slide, but no, we don't. Let's do another problem. 95% confidence interval, the mean difference, 0.01 to 0.01. Average standard deviation is 1 again. So my 95% confidence interval of the Cohen's d is negative 0.01 to positive 0.01. My interval includes 0, right? So P is greater than 0.05. That's not small, so it's not significant. No big deal there. Now let's do the same kind of thinking. Do I have precision in my estimate? So here's what I see is that it's not a medium effect or an average effect for or against my hypothesis. It's not a large effect for or against my hypothesis. What I do know is that it's either a small effect against, a small effect for, or no effect. Those are the possibilities. Do I have precision in here? What do you think? Go ahead, say out your answer, and I'll tell you my thought in about 5, 4, 3, 2, 1. Say it. I think we have okay precision here. It's not great. It's not as bad as the last time. It's definitely not as precise as I want, but also there's realities of our science. This is an okay precision. What do I know in this case? Well, worst case, it's a small effect against my hypothesis. Best case, it's a small effect in favor of my hypothesis. What did I just say about small effects? For the most part, that's basically telling you there's no difference. So essentially, like, my precision is all around that area where there's no effect. So basically, I know I have an okay level of precision, and I know that there's basically no effect. Now, I'm still on the previous example, and I want to tell you something. 0.01 is 20 times smaller than 0.2, right? 20 times smaller than small. Let's be real. That's really not small. So in this case, there's not hard and fast rules. When I'm thinking about this, I'm like, oh, wow. Like, yes, there's a small effect. Is it fair to say that 0.01 is small? No, that's not fair at all. That's just sort of like math rounding error. Essentially, there's no effect here. And in this case, I know, right, if you're using this interpretation, I know that my only interpretation on these 7 different pie slices is there's no effect. That's the only one it can be if you take this extra thought that I had, right? 0.01 is 20 times smaller than 0.2. Do I have precision? Yes, I do. Yes, I do. I have precision. Now, what I just did here is one of the special reasons that I really enjoy confidence intervals. I use this 95% confidence interval of the Cohen's d to suggest that two means are the same. Now, you probably don't know this. This might be your first statistics class where you're thinking about publishing in science and stuff like that. But I got to tell you, most of the time we just aren't allowed to say two means are the same, right? That our mean difference is essentially zero. But here you can see there's a strong logic in this specific made-up example for me to be able to say that. Essentially, like, there's no effect here. Worst case scenario is the tiniest effect that ever existed in the face of psychology in favor of my hypothesis, well, against my hypothesis. Best case scenario, it's the tiniest effect ever in psychology in favor of my hypothesis. It's the tiniest effect ever. These two means are practically the same. But you know, some of us know that we're not allowed to say two means are the same with the statistics that we use. Well, in fact, we're not allowed to say it with p-values. That's really the rule. So by adding this confidence interval stuff, I'm going to be able to convince a reviewer of my article that yes, he did find that the two means were basically the same. Now, here's how I'd write it up. While it is axiomatic, that just kind of means generally accepted in principle that we should never say that two means are perfectly identical when the p-value is greater than 0.05. The 95% confidence interval of the Cohen's d's presented above indicates that the likely population Cohen's d is between two effect sizes that are considered practically nothing. By definition, 95% of the time, your confidence interval includes the true population, and thus, if this interval replicates in study 2, I will feel confident in stating that these two means are practically the same. You can see I did some editing there. I want to show you that everybody has bad first drafts, and this was a first draft. And every time I read it out loud, I catch errors. This is also a point for you to learn how to write better. Reading it out loud, you can catch errors. That whole however thing that I threw in there, I saw that was bad, and so I was like, didn't read it. But I think it's good to see this work in practice. Not everything's a finished product. You as students have to start to learn how to make these products, how to clean them up. So there's two things on this slide. One, read your work out loud, revise it, fix it. You'll hear the errors. I could see mine right there. The other thing is with logic and argumentation, you can make claims that you can't make with just p-value alone. And this is one of the reasons why I'm really focusing us on these 95% confidence intervals of the mean difference. Let's do another problem. 95% confidence interval of the mean difference, 1 or 2. That we know the mean difference is 1.5. Our p-value is less than 0.05. So we know small is significant. So that is a significant effect. Less than 0.05, small p-value is significant. Not small is not significant. So the average standard deviation is 1. I'm making these numbers up. That's just a little hint there. So let's see, our 95% confidence interval of the Cohen's d is from 1 to 2. So the worst case scenario is a large effect in favor of my hypothesis. The best case scenario is a large effect in favor of my hypothesis. What do we see? Right? We see that that's a very precise estimate. Of the 7 possible effect sizes, the population value of my mean difference is likely only a large effect. That's it. That's very, 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 well, let me ask you, do we have precision in this interval? Yes, we have precision. Let's do another example. My 95% confidence of my mean difference is 0.01 to 2. Your mean difference is roughly 1.005, excuse me. My p-value is less than 0.05. Small is, insert the word, significant. Yes, it is. My average standard deviation is 1. I'm making up these numbers. We'll get to real numbers in the second unit. But ultimately, when I convert this to a 95% confidence interval of the Cohen's d, you'll see that my Cohen's d ranges from 0.01, one of the most tiniest, smallest effect sizes you could ever have, to 2, one of the largest massive effect sizes you can ever have, and both of them are in favor of my hypothesis. So what do we see here when we're looking at my pie chart to figure this out? We know that it's either a small effect 4, an average effect 4, or a large effect 4. Do we have precision? What do you think? Right? And this one's a little bit debatable. Do we have precision? For me, I'm saying our precision is okay. Why am I saying my precision is okay? It's like, well, essentially, I do know that the effect is not 0. I know it's not the opposite of what I predicted, so I do know the effect is in the direction that I predicted. I'm confident that the population mean difference and the population Cohen's d that I'm interested in are in the direction that I predicted. So that's actually pretty cool, right? That's like a good... That's like a good thing. I got some knowledge there, right? Like, I know the effect is not 0. I know it's not against my hypothesis. Now, my hypothesis is the one I predicted when I designed this study. But ultimately, I really wish I mean, if it's my science, I really wish that small value wasn't in there and that, it was between medium and large. I really wish it was either precise at medium or precise at large, right? That would be the best estimate. But, here I'm dealing with the fact, well, it could be like the smallest effect in the world. At least I know it's not 0. I don't have the best precision. It's okay. But at least I know it's not 0 and it's not the opposite of what I predicted. So that's better than what it could be. So, I'm saying it's okay. There are no hard and fast rules here. You got to think. You got to use your mind. You got to look at your study. You got to set your own criteria. And what I'm seeing here is that, I know that the hypothesis wasn't disproven. In most cases, it's supported. The worst case scenario, this could be the tiniest effect in the world. But at least I know it's not 0, and at least I know it's not the opposite of what I predicted. Best case scenario, massive effect. Now, remember, 0.01 is 20 times smaller than small, right? But my p-value is telling me that we know it's not 0. But you can see I changed that little green arrow just to indicate that it's getting real close there, right? It's getting real close. And for me, it's just kind of hard. You might even color that in green, but I'd say with your p-value knowledge, you shouldn't color the whole thing in green. Maybe shade it, whatever green and red make together. I don't know, brown probably. But, it's difficult. It's difficult when you're making these decisions on how precise your study was, how good your measurement error is. That's what we're asking right now. How poor was my measurement error? Right here, my measurement error is pretty bad. And I'm going to run another experiment to see if I can get it down. That's for sure. That's what I'm learning here. But also, I do know that what I was saying before, like, it's not 0. It's really, really, really close to 0. It might be, it might be so close to 0 that it's essentially 0, but it's not technically 0. So, I'm going to call this new way to think about it. So what do I know? It's barely okay. It's barely okay in precision. I know that my effect could be a small effect 4, an average effect 4, or a large effect 4. So I know that my hypothesis is supported. That's what I know. But, is an effect that matters? No, it includes that small effect. That's essentially bad, right? So, it's less than the small effect. Ooh, like my worst case scenario is there's nothing really here that's worth promoting in public policy or promoting in medicine. My best case scenario, massive effect in favor of my hypothesis, and that's good. So remember, this 95% confidence interval was from a very, very small effect, a 0.01 effect, to a very large effect. And in that previous example, a few examples back, I said that, oh, this is 20 times smaller than the cutoff for small. So that's essentially approaching zero. It's not technically zero, but it's so close to zero that it might as well be. And so, my precision is still okay, but I also want to point out that this is all you know when you say your p-value is less than 0.05. And it doesn't improve by providing smaller p-values. It really doesn't. All you're doing is saying, oh, well, when you read a scientific article with a p-value less than 0.05, all you know is that the effect could be a large effect, it could be an average effect, it could be a small effect, or it could be so small that it's basically zero, but just a hair on the other side. This is why a lot of us are moving away from p-value only calculations. And I know it's how you were taught. I know it's how we get published still. But that's improving. I know it's important to science in general. But also, ultimately, I want to show you how imprecise it is. Without that confidence interval, the mean difference, without converting it to a Cohen's d, my preferred method of understanding it, all you know is that your effect is not zero and it's in line with your hypothesis. But that effect could be tiny. That effect could be massive. Do you really want people to develop public policy on your research when all they know is what we're seeing in front of us? That our effect could be so small, it's approaching a no effect, but it's just a hair on the positive side of the no effect of 0.000001. That's all we know with p-value. Could be a massive effect, could be the tiniest effect ever. P-value less than 0.05 doesn't mean something's large, doesn't mean something's worth putting into practice, doesn't mean medicine is worth making happen. That's where I'm scared with what's going on right now with our clinical trials for our vaccine. Okay, P's less than 0.05, and is that how we're going to evaluate the public policy? I really hope not, because I know I'm not the only one thinking about this. But I will look at that data when it comes out, and I'll help you interpret it. But ultimately, I hope you're starting to see, oh, p-value is very limited. It just tells me that I don't have a zero effect, but my effect could be very close to approaching that zero effect. So that's why we need to have more than just the p-value. So what do we know? When we do a p-value calculation, the only thing we know is that our mean difference is not zero. We don't know that our mean difference is large or important or valuable or putting into practice. We have no estimate of precision of our mean difference when we just have the p-value. And so it's not the best statistic, in my opinion. With our effect size, what do we know? We know our signal-to-noise ratio, we know standard deviations apart, and we know small, average, and large in our field. We also have no estimate of precision. Our 95% confidence interval, the mean difference, we know p-value. We do not know effect size, and we also know precision, but it's difficult to interpret. 95% confidence interval of the Cohen's d. We do know our p-value. We know our precision. Easy to interpret, in my opinion, if you follow my little pie chart rule. And we also understand everything in terms of effect size, which are relative to the average effects in our field. So we know quite a bit right there. There is also a 95% confidence interval of the p-value, which I won't show you how to calculate, but it's really not that hard. Essentially, you take your lower limit and your upper limit of your 95% confidence interval of the mean difference and just figure out what the p-value would be if that was your sampled mean difference. But they're not that tricky to calculate. They're just kind of a pain to calculate. You got to do it by hand. But they will also make you cry. But they might be the way that we should go. If you really believe in p-value and you don't like my methods of 95% confidence intervals of mean differences or 95% confidence intervals of Cohen's d, I will challenge you to do a 95% confidence interval of a p-value. I will not only challenge you, I will help you calculate it. But ultimately, right, I think it's important to see, what do we know? P-value, not very much. Effect size, we know one thing. I'd say it's better than p-value, but that's me, right? We know a little bit more. But you could also say not very much. With the 95% confidence interval of the mean difference, we get p-value and precision. 95% CI of the Cohen's d, we get p-value, precision, and effect size. And just so you know, there is a 95% confidence interval, the p-value, for those that believe in p-value very strongly. And I think it's important to understand that our mean difference is sampled with error. And so our p-values, if we really care about that, we should have those. We should convert those into a 95% confidence interval as well. What else do we know? I didn't actually mention this for my 2 confidence intervals, but we know that the true population value likely falls in that range. With the p-value, we don't know that. With the effect size, we don't know that. Those are what I call point estimates. Any point estimate is likely to be completely wrong. What do you think the probability is that your mean difference is the exact mean difference in the population? Very low. What do you think the probability is that your p-value is the exact p-value in the population? Well, p-value in the population doesn't exist, but still very low, right? The effect size. What's the probability that your effect size is the true effect size for your population? Very low. But we add the precision estimates, we add the intervals, and we start to have a better understanding. So what do I want you to do in this class? I really want you to just think about your data. P-values have turned us into zombies. We're like, the world's black and white, our science is black and white. No, it's not a significant, non-significant world. It's much more complicated than that. And as we started to realize this, we started to use more complicated statistics. And I think the very best entry into these complicated statistics is the 95% confidence interval of the mean difference. It's just so valuable. And then for you to interpret that 95% confidence interval of the mean difference, convert it to a 95% confidence interval of your Cohen's d. This just allows it to just be easier to interpret. Oh, worst case scenario, this is a small effect against my hypothesis. Best case scenario, this is a small effect in favor of my hypothesis. What do I know? Well, essentially, I know that these worst case scenario, there's no large difference there. That difference is basically meaningless. Best case scenario, that difference is basically meaningless. So essentially, I know I've basically found no difference. If I get you on the poster session, you need to be able to talk about the precision of your effect size estimate. Now I'm going to say something. Your mean difference is a measure of effect size, and so is your Cohen's d, but I'm going to want you to think through your data. And you know what? The sad reality is, especially if you go back 10 years, most folks don't report their confidence interval of their mean difference. Most scientists were happy choosing publication over truth. They were happy knowing that I might have the smallest difference in the world, or I might have the largest difference in the world, p less than 0.05. They were happy presenting that out there for activists to take up and use, for public policymakers to take up and use. And I'm telling you, that's not ethically okay to be happy with. That's not fine in my world. It's not okay. It's just not, right? And so like p-values, I'm okay with p-values, but p-values as your only method of statistics, that is not okay. That is not giving me enough information to evaluate if you actually have precision in your estimate to actually evaluate what the likely true population value is. See, go back to that original hyperbole that I shared earlier. We're trying to do something that only gods can do. That is it. We're trying to do something that only gods can do. And if we cheat, if we don't think about it, we're going back to the realm of humans. And this thinking is hard. It's hard for me. I've spent about 20 years, I've definitely spent 20 years thinking about stats. Just in general, trying to understand it. My first semester in undergrad, in my biology and my chemistry classes, right? Like I had to understand p-value and all this stuff, and I was taught what it was over and over and over again. But nobody taught me about precision. Nobody taught me how to calculate it, and nobody taught me that this is a problem. And I don't blame them, because we've only learned recently that this is a problem. Now, currently we have I just have two abstracts in front of you from real articles that you might want to look up. Number one for neuroscience, a lot of my neuroscience students think, oh, that's psychology. Psychology is BS. Psychology is crap. It's really just psychology that's having these problems. Well, they've looked at your field too, and what they find is that your studies have too small of an N to actually estimate the true population values, and your estimates are widely positive in favor of your hypothesis. That is, with these small sample sizes, neuroscientists are creating a field of neuroscience that just isn't true. So, neuroscientists, you are not absolved from any of these critiques. Now, in psychology, we've actually done some large-scale studies where we try to take studies from the field, we randomly sample them, and we do really large replication studies, massively large replication studies with like 500 people per study, stuff ridiculous like that. And what we find is that less than half of our science replicates. And that's in psychology. You're going to have a worse problem in neuroscience, or at least an equal problem in neuroscience, because the small sample size, when you read a paper with 3 mice, with 3 monkeys, with three observations per group, you got to start questioning, is that good science? No, it's not. And you can read the papers on it if you want. In our field, is p-value good science? Is our stuff replicable? No, we have the same problem. And I will argue that both of these problems are related to our lack of focus on precision and our lack of focus on error in our measurement. So this graph is going to help us understand why small sample sizes and why p-value statistics are a problem for science and for truth. But in order to get there, I got to explain to you what we call the Monte Carlo study. Now, the Monte Carlo study is the way we test our statistics. When you run a study, you have to go out and get people, and you have to run them through conditions, and you have to measure things, right? That's how we do it. That's what you're being trained to do. Now, that's so we can find out what psychological things are happening in people in the real world. Now, when we want to test which statistics are the best at finding truth, what we do it the opposite way. So we create a population value of numbers that represents each human in the world. You could say it's 4 billion. You could create a database with 4 billion numbers in it, right? Well, when we do that, we create a database that has a known value. In this example, this database has a known mean difference of 10. So the true population mean difference is 10 in this specific made up data set that's supposed to represent all people in the world if there's an effect. Now, why 10? Well, this 10 is accompanied with a standard deviation of 20. This was set up to have the average effect size in the field of psychology and and behavioral science and neuroscience, okay? So we have what we know as the medium effect, so they set it up that way. The population mean difference, we know it because it's just numbers made up in an Excel file, right? So we know the population mean difference is 10. We know that this is a quote-unquote significant difference, and we know the true population value is 10. And so then what we do is we run our statistics to see, do they lead to truth? Okay? Now, how would we do that? We would sample a small subset from our population, and we do that for control and experimental group. We know the true mean difference is 10, but we're going to see what our sampled mean difference is and have all that fun, right? That's what we're doing. Then, right, we run our p-values and we run our 95% confidence intervals of the mean difference. With the p-value, we expect significance. With the 95% confidence interval of the mean difference, we expect 10 to be included in the interval 95 out of 100 times. But this is how we test if a statistic works. It's called a Monte Carlo study. You create a distribution of data with a known mean difference. You sample from that population of data. You run statistics. You see, did the statistics lead to truth? It's kind of a nice flip on how we do science, but it's also pretty cool. It's like pretty ingenious. It's like, oh, Do my statistics work when I have a skewed distribution? Do my statistics work when I have outliers? Do my statistics work? You could use this in so many different ways. Do my statistics work when I have a bimodal distribution? All that fun stuff. But right now, they said, do our statistics work when we sample 32 observations per condition? So that'd be 64 total. This is done, this specific Monte Carlo study, and this graph represents the Monte Carlo study done when there are 32 participants in the control condition and 32 participants in the experimental condition. All right? And I want you to think like about your sample size. Your sample size is probably nowhere near this. Let's see if how many times our p-value leads to truth. We've already discussed that our p-value should be significant, right? So small is significant, so we expect less than 0.05. So let's look. The first experiment they ran found a significant effect. That's pretty good. The second one, they put a question mark there, but I'm saying, nope, that's not significant. I cannot publish that. So now you have 50% leading to truth here. The third one, significant. Okay, 2 out of 3. Fourth one, non-significant, 2 out of 4. Fifth one, non-significant, 2 out of 5. Sixth one, significant, 3 out of 5. And you can, I don't have to walk you through all this, but I will. Non-significant, you can keep tally. Number 7, non-significant. Number 8, significant. Number 9, that's the difficult one, right? 0.05. Let's just leave it out. We'll keep it out of 24 because it's just a little... Like, is 0.05 significant? Is it non-significant? Let's just leave it out because it can go either way. Next one, non-significant, significant, significant, non-significant, significant, non-significant, 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 significant, 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 non-significant, non-significant, significant, non-significant. Let's count what percentage of the 24, I'm dropping the perfect 0.05. What percentage of these found truth? Remember, truth, this is a real effect. There is a real effect in the population. What percentage found truth? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 out of 24. 11 out of 24 found truth, included truth. That is worse than a coin flip, my friends. That is worse than a coin flip. Isn't that scary? Right? 11 out of 24. 46% found truth. If you have a balanced coin, you're better off flipping a coin than using the p-value to test your hypothesis. That is a sad reality. So if you're a p-value person, you should probably switch to 95% confidence intervals of the p-value. And maybe you want it so that your lower limit has to be less than 0.05. Or, your lower limit has to be at least less than 0.05, essentially. And your upper limit has to be even less than that. That's such a horrible description. But if you think about a 95% confidence interval of a p-value, you want it to be from 0.05 to 0.000000000 small, okay? But wow, less than 46%, that's horrible. I wouldn't use that. And this is for studies that are better than the studies that you're doing. They have more participants. The Monte Carlo simulation says you should not use p-value to find truth. How well does confidence interval do? Remember, the true mean difference, true sampled mean difference is 10. Does the first interval include the true value? Yes. Study 2, yes. Study 3, yes. Study 4, yes. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, yes. 17 does not, but look how close it came. Look at how close it came to including the true value. So close, but it still didn't. So that's one failure. Then we got 18, 19, 20, 21, 22, 23, yes. 24, no. 25, yes. 23 out of 25 included truth. 92%. So we predicted 95% of these studies would include truth. It's really 92. maybe it'd get better if we ran 75 more, but ultimately, which one's better at finding truth? P-value or 95% confidence intervals of the mean difference? To me, it's very clear. You do not have 64 participants in your study or 64 observations in your study. You might, but also your studies have 4 or more conditions. A 2 by 2 is the bare minimum. So you would actually need more like 128 to even be as bad as this specific Monte Carlo simulation is. I'm going to say it again. You might as well flip a coin. Okay, if you're going to do p-values, you might as well flip a coin. So, I think this is a call for us as a field to do better. Do better than those that came before you. I know that p-value is comfortable. It's easy to say this is either true or false. And now you know why we shouldn't do things that are too good to be true. Because in this case, you're better off flipping a coin than running a p-value. But your 95% confidence interval, the mean difference, includes truth most of the time, includes the true mean difference most of the time. And that's beautiful and that's powerful. And when you look at those confidence intervals of the mean difference and they're super spread out, you have to ask yourself, how can I improve my confidence interval? How can I reduce this spread? And that's the challenge that is standing in front of the field. And it's weird. It's weird for me because not that long ago, I was just entering the field, it felt 16 years ago in 2003. But, I was taught everything that you probably learned in high school. P-value less than 0.05, that's significant. Oh, it doesn't really matter. Your confidence interval, the mean difference doesn't really matter. Significant is significant, and that means important, right? That's basically how I was taught to process this data as well. But now we're learning that's false, and we can do better. So what is your homework? Below, you will see a series of confidence intervals of the mean difference. Assume the standard deviation is 1. I have that on the problem. Tell me everything you know. What's the sampled mean difference? What's the p-value? What's the precision? That's the convert to Cohen's d. You have good, okay, great, poor precision. Let me know. Let me know what you know. Okay? Let's see it in action.